So for this little section, all we'd like to do is keep that idea in mind about how partial molar volume works and apply it to other state functions, in particular extensive state functions. Those are functions in which that quantity depends on how much you have. And I've given some examples here. We already said volume, the internal energy, the enthalpy, Gibbs energy. These are all quantities that depend on how much of that material you have. So here's the new definition. We want to define something that we're going to call chemical potential. They use the Greek letter mu, subscript I. So the I is referring to what substance you're talking about. So this chemical potential is the same thing as the partial molar Gibbs energy. So the bar over the G is, just like we used in the last section, referring to this partial quantity. So the partial molar Gibbs energy is going to be dG over dN sub I. So how much the Gibbs energy changes when you add an amount of substance I, in this case, to a mixture. Now you're keeping the temperature, the pressure, and the amount of any of the other substances constant. Let's just think of something simple like a two-component system. So let's say water and ethanol. The Gibbs energy of that mixture is going to be the sum of two terms. The sum of, let's say, the amount of water you have times its partial molar Gibbs energy of water plus the moles of ethanol you have times the partial molar Gibbs energy for the ethanol. So the total solution Gibbs energy is the sum of these two terms. It's the sum of the contribution from each of the components, just like we did for volume. Now we know how important Gibbs energy is from our earlier studies of thermodynamics in chapters 4 and 5. This is going to set us up for developing a criterion for spontaneity or equilibrium in a multi-component system. So in the same way, remember when we looked at Gibbs energies and we would decide, oh, does this component prefer to be in the gas state or the liquid state in this temperature and pressure? You judged it by the Gibbs energy. Again, if you need to review, take a look at chapter 5. Now we're talking about knowing Gibbs energy being the driver or the criterion for knowing if something's going to happen spontaneously when you have a mixture. So this gets a little theoretical, but follow with me. Consider a sample of component I in some state, and that state is A. So let's just think of an ice cube. So component I, water, in some state. Now by this I mean it could be a phase or a chemical combination, and you want to know if it will spontaneously transfer into state B. So for a process carried out at constant temperature and pressure, the change in Gibbs energy would be the difference between the Gibbs energy in state B and the Gibbs energy in state A. If the chemical potential of state B is less than the chemical potential of state A, then the dG term will be negative, and therefore the transfer is spontaneous. So the kind of process you could talk about is phase change, diffusion, solution formation, etc. You always are going to go spontaneously from a higher Gibbs energy to a lower Gibbs energy. This explains why chemical potential is a good term. So you might think of, again, let's say a mole of water is the component I. Now, is the mole of water by itself going to spontaneously make a solution with, let's say, ethanol, it being in state B? Now we know that those solutions are miscible, so that what this is saying is that the chemical potential of the water, while it's in solution, state B, must be lower Gibbs energy than when it was by itself. And so you could have any process that I mentioned here. It could be a phase change, it could be doing a chemical reaction, it could be whether or not something will make a solution, simply by comparing the Gibbs energy of the component in one state versus the other state.